So welcome to you all to my tutorial class. I am your PMRF TA Songkhonarayan Chattopadhyay for the course NPTEL Engineering Mathematics 1, and it is our 7th live interaction class, and the course code is NOCMA88 and instructor is Professor Jitendra Kumar. He is a faculty at the Department of Mathematics, Indian Institute of Technology, Ropar, and I am also doing my PhD. Here at IIT Ropar. So in today's class, from today's class now on, we will start to learn about the concepts of multiple integrals. So our domain of study for like this 7th week or in the next 8th week, we will mostly discuss about multiple integrals. So till now we have learned about some basic properties of differential calculus with a single variable. Then we have learned about limit, continuity, differentiability and all, about function of several variables, be it 2 variables or like 3 variables or 4 variables. You can extend the notion. And the next few class we have learned about like maxima, minima, Taylor series approximation, as well as Taylor series approximation, as well as constrained maxima, minima, etc. And in the last class we have discussed about improper integrals. So today's class and maybe in the next class we will discuss a bit about what do we mean by saying multiple integrals. Like in what we have calculated till now integration, we did integration considering Riemann integrations, right? So then in improper integral we have extended the idea of Riemann integration to capture the two types of singularities that may appear in certain problems. So as we have extended our idea of limit, continuity and differentiability for function of 2 variables or function of 2 variables or 3 variables some cases. Similarly, we can extend the idea of integration for function of 2 variables as well as function of 3 variables. So when we do integration with respect to function of 2 variables, then we will encounter double integrals, and when we will try to integrate function of 3 variables, then we will encounter mostly triple integrals. So see, first we will just go through some basic concepts about multiple integrals. So volume of a solid of revolution. So what does it mean? That the solid obtained by rotating a plane region about a straight line in the same plane is called a solid of revolution. The line is called the axis of revolution. See, for example, this is the 0x axis and y equal to root x is the your parabolic curve, right? Now if you this half part of this parabola, if you rotate it like this, okay, in either in counterclockwise direction or in anti-clockwise direction, just rotate it. Okay, so here take the 0 to 4 and you are inscribing the sectorial area, and now you are rotating this sectorial area. So when you rotate the sectorial area around this x-axis, you will get this type of parabolic shape, paraboloid type shape. Now you are to determine the volume of this parabolic shape. Is my idea, is my point clear? That what we want to do, see here it is x-axis and it is y-axis, and we have plot the y equal to square root of x. Now our consideration of interval is 0 to 4. So if you rotate this inscribed area in this around this axis in this direction, Okay, so eventually what you will get, you will get this type of paraboloid shape, right? And now you are to determine the volume of this paraboloid shape. So suppose the region is bounded above by the curve y equal to fx and below by the x axis, where a is less than or equal to x less than or equal to b. For your graphical illustration, we have kept this as y equal to square root of x, and our a is 0 and b is 4. So when deriving the theory, we will okay, so while deriving the theory, we will we will use this y equal to fx and below by the y-axis, where a is less than or equal to x and less than or equal to b. To find the volume of the solid so generated, we divide the interval ab into n equal parts. Let the partition be a equal to x0 less than x1. So it is actually a monotone increasing sequence, where the last 2 points are actually the 2 end points. On the ith subinterval, that is on the subinterval xi minus 1 to xi, what we will do, approximate the volume of the slice disk generated here. Now how does this, the volume of the disk will be pi, that will be the volume of a disk is pi r square h. How? That it is actually a cylinder type of shape, right? So its surface, its area is pi r square and its height is h. So it will eventually end up you giving the volume is pi r square h. Now see that what is the this what will be your radius here. The radius will be rx equal to square root rx equal to fxi star for any point that lies in between this, right? So why it is like that? Because the slice is a portion of a cylinder whose cross section with a plane vertical to its axis is a circle. So what we are doing just it is pi into fxi whole square into, you have to determine the small width of this disk. This is xi minus 1. So it will eventually give you pi into fxi stars whole square into xi minus 1 for a point this. So volume of the solid of revolution is approximated by this sum. You just take summation from I equal to 1 to n. So what we are doing here, see, then the volume of the solid of revolution is approximated by the sum equal to this, because you are determining that all such disks possible from 0 to 4, say for here a to b. So then the volume of solid of revolution is the limit of the above sum, where n tends to infinity. And if you just sum this and if you take the Riemann sum, then if you take limit n tends to infinity, then it will eventually give you the integration. So what is the formula here? The formula here is, if you are to determine the volume of revolution by the curve y equal to fx from the point a equal to b, then the surface of volume of revolution, the solid of revolution is, the volume will be integration a to b pi f of x whole square dx. Okay, so now we will try to solve for our problem. See, first see example 2.1. So our governing formula is integration a to b pi into fx whole square into integration with respect to dx, right? So we are to here our fx is square root of x, and our domain of integration is 0 less than or equal to x less than or equal to 4, and the x axis is revolved around this is typo, sorry, and this y equal to root x, this curve is revolved around x axis. Okay, so how we will determine the required volume of revolution? That v equal to integration 0 to 4 pi square root of x whole square dx. Now square root of x whole square, this means x, so you are doing integration from 0 to 4 pi x dx, so you will eventually end up getting this is x dx, integration is x square by 2. So if you integrate it from 0 to 4, you will get it as 8. So overall your volume of revolution is 8 pi. So if you consider this type of paraboloid using governed by just rotating this area, you will end up getting an solid of volume 8 pi. Now similarly, if you want to determine the volume of the sphere x square plus y square plus z square plus equal to a square, this is a equal to 1. So how the circle is sphere is generated? See, instead of this parabola, if you take semicircle, this type of semicircle, and if you rotate it, what you will get? You will eventually get the sphere. Instead of parabola, if you take semicircle, this type of semicircle, right? This type of semicircle, and if you rotate the semicircle, you will get the sphere. Okay, so are you with me? Okay, so we think of the sphere as the solid of revolution of the region bounded by the upper semicircle x square plus y square equal to a square, where y is greater than or equal to 0. So here minus a less than or equal to x less than a, the curve is thus y equal to square root of a square minus x square. Then the volume of the sphere is integration minus a to a pi of this whole square dx. So if you just integrate it, you will get that the volume of the sphere is nothing by 4 by 3 pi a cube, the formula which we have learned from our high school, right? This formula we have learned right from our high school, that the volume of a sphere is actually 4 by 3 pi a cube. Now actually how we are determining this? We are just taking this as a the sphere as a volume of revolution of the semicircle around the x-axis. That's our main idea. Now similarly, see example 2.3. Find the volume of the solid obtained by revolving the region bounded by y equal to square root of x and the lines y equal to 1, x equals to 4 about the line y equal to 1. Okay, here there is one typo. Okay, this is x, this should be x equal to 1, not y equal to 1. This should be x equal to 1 to x equal to 4, and here we are revolving this axis square root of x about the line y equal to 1, right? Y equal to 1. So this is nothing but you are translating this x-axis into here. Okay, so this distance from this x-axis is square root of x. So what is the distance from this y axis, y equal to 1 straight line? The distance is square root of x minus 1. So and your domain of integration is 1 to 4. So v equal to 1 to 4 pi of rx whole square dx. This is 1 to 4 integration pi square root of x minus 1 whole square dx. If you integrate it and if you just take just a minus b whole square formula, you will get it as x minus 2 square root of x plus 1 dx, and if you simplify it, you will get it as 7 pi by 6. Now another one interesting problem. See, find the volume of the solid generated by revolving the region between the y-axis and the curve xy equal to 2, where y this is belong to 1 to 4. So till now we have discussed formulas about evolving of areas around x-axis. Now the concern is, if you are to supposed to determine the volume of the solid generated by revolving around y-axis, so how to tackle this thing? To tackle these things, the formula is same. Just instead of rx, put ry, that is you are to determine distance from y-axis, and obviously the limit of integration will be 1 to 4 dy. So here it is xy equal to 2. So what is ry? So if you just express x in terms of y, you will get x equal to 2 by y. So ry is 2 by y, you take whole square, and eventually you will end up getting this answer to be 3 pi. So see how easily you can determine the say area inscribed by the volume of this type of complicated geometric shape. Similarly, find the volume of the solid generated by revolving the region between the parabola x equal to this and the line x equal to 3 about the line x equals to 3. Okay, so first of all, this is this x equals to 3 line. This is your axis of revolution, right? This is your axis of revolution. And if you inscribe this x equal to y square plus 1, you will get it as this is your x equal to y square plus 1 curve. And how to, so it is actually giving you, if you see, this is the curve, and ry, this y square plus 1, what does this y square plus 1 gives? This y square plus 1 gives your distance from this y axis, right? This is your distance from y axis. Now if you are to want to determine the distance from this straight line, now the distance between this y axis and this straight line is 3 unit. So if you minus this distance y square plus 1, you will eventually get your the distance around this axis. So it will eventually give you 3 minus y square plus 1, so 2 minus y square. Now revolve around it, and your this integration will be from minus square root of 2 to square root of 2, and the distance you have managed to put it as like 2 minus y square dy. So this is 64 into pi into square root of 2 divided by 15. Okay, now see, if the region which revolves, see, this is y axis, this is x axis, and if you evolve this type of sectorial area, so there is a gap between x axis and this area, right? So if you revolve this area, you will get a solid. In between there is some hole, because there is no area inscribed in this white portion. So if you just rotate this sectorial area inscribed between these two things, you will get a holes inside the solid. So what is the formula? It is y equal to rx curve, it is y equal to rx small rx curve, then the volume of revolution will be a to b ax dx, where ax is nothing but pi of, so the area will be pi into capital Rx whole square minus small rx whole square into dx, because first you have to determine the area inscribed by total this term, and then you determine the area inscribed by this person and x axis, and then just minus the smaller one from the larger one, you will get this sectorial area. Find the okay. Similar question is, the region bounded by the curve y equal to x square plus 1 and the line xy equal to 3 is revolved about the x axis to generate a solid. Find the volume of the solid. So it is y equal to x square plus 1 and here y is equal to 3 minus x. So 3 minus x is our larger proportion. 3 minus x is greater than x square plus 1. Okay. Now the limits of integration are obtained by finding the points of intersection of the given curves. Okay, so the when x square plus 1 equal to minus x plus 3, this condition will eventually give you the intersection points and the limits of the integration. So the required volume is v equal to minus 2 to 1 pi equal to minus x plus 3 whole square minus x square plus 1 whole square dx, and if you determine this integration, you will get it as 117 pi by 5. This is simply just execution of this formula. Similarly, you can extend this concept around y-axis also. So I am skipping this question because it is bit easy, because you have to just use the formula that here it is y equal to x square, but you have to find out solid obtained by revolving the region bounded by the curves this about the y-axis. So you have to write it as x equal to square root of y and x equal to y by 2. Then you have to determine that how this sectorial area is this, then limit of integration is 0 0 and 2 4. Then you have to just move this tiny slice around y-axis when your integration is 0 to 4, and then you have to just minus them. So these are some complex problems. Okay. Okay. Okay, this is also solid. You have to find out the volume of the solid generated by revolving about the x-axis, the region bounded by the curve this. So it is pretty straightforward. You have to just integrate from 0 to 2, and the function is fx is given as 4 by x square plus 4. You have to just take square of it, so you will get it as dx, and if you just integrate it, you will eventually get as twice pi cos square t dt, and this will be your formula. You just go through this portion. There are like many you can easily understand it, that how this graphical representation is helping us to determine the volume, how we are trying to determine like this type of parallelepipeds we are forming, and then we are taking the mesh to be smaller and smaller so that we can approximate this thing, and eventually using the help of integration as we are getting the volume. See one question, that find the volume V of the solid raised over the rectangle this and bounded above by the plane this, we proceed as follows. Okay, so we are to find the volume V of the solid raised over this. How to determine? You have to just use integration. How you are using integration? See, the shape of this plane is like that, and you are to like integrate them in between the square domain 0 to 1 to 0 2. So if you just use, see, ax is 4 minus x, so z is 4 minus x minus y. You have to just integrate 2 times 0 to 1. So it is actually an implication of double integral. So if you just use so see, we are to trying to determine the integration from 0 to 2. There are, see, I am once again discussing that how you are trying to determine this thing. Is my screen visible right now? Okay, so we are to find the volume V of the solid raised over the rectangle R 0 to 1 to 0 to 2 and bounded above by the plane z equal to 4 minus x minus y. We proceed as follows. So we are to determine the volume, so we have to just take integration. The integration for x axis will be 0 to 1 and integration for y axis will be from 0 to 2. So you have to just integrate z, whose expression is given by 4 minus x minus y, in between this rectangular slide. So this is 0 to 1, 0 to 2, 4 minus x minus y dy dx. So this type of expression left is double integral and on the right is an iterated integral. This type of term we call it in mathematics iterated integral. Now see, first there is one theorem, important theorem. The proof is not important for you guys. It is just called Fubini's theorem. So what does Fubini's theorem means? That Fubini's theorem tells us that if R be a rectangle a cross b to a comma b cross c comma d, then if f is a real valued function from this rectangular region and it is continuous, then the value of the double integral will be same as that the value of iterated integral. So for multiple integral, the value of multiple integral to be equal to the iterated integral, you have to just need the fxy to be continuous on that region. Now see, this is 0 to 1, 0 to 2. So in this rectangular slide, this function is continuous. It is a simple linear function. Now what you will do, we will first integrate between 0 to 2 with respect to y. Okay, you will just integrate from 0 to 2 with respect to y. And when you are integrating with respect to y, just keep x as constant. So when you are integrating with respect to dy, you will get it as 4y minus xy minus y square by 2. And you take the limit from 0 to 2, put these limits instead of y, then it will reduce into a function of x. Then you take integration with respect to dx. See here how they are solving this. How they are solving it. See, evaluate r, and r you are integrating. R is actually rectangular slice 0 to 2 cross minus 1 to 1. So this is you want to integrate in this rectangular slice. So if you take this is x and y. So first, like, integrate in between 0 to 2, and it is continuous in between this. So using Fubini's theorem, this multiple integral can be reduced in this iterated integral. You take integrate with respect to dx. So if you integrate with respect to dx, you will get x minus 2x cube y. Now put x equals to 0 and x equal to 2, you will eventually end up getting 2 minus 16y dy. Now once again integrate with respect to y, and you will get it as 4. Also you can take it reversing the order of integration. So if a function is continuous, where is Fubini's theorem? So if a function is continuous, then you can use iterated integral. You can swap the order of integration. Okay, so see, y sin xy. So like this type of swapping of integral limits, that how you are trying to solve between dy, or you are trying to integrate with respect to dy first, or integrate with respect to dx first. Make this decision upon that which type of integral is easier to compute. See, it is y sin xy dx dy. So the region for integration of y is 0 to pi and x is 1 to 2. So what is happening here, that this type of function, this sinusoidal or cosine function, the volume you are getting to be equals to 0. Why the volume you are getting to be equals to 0? Because the volume inscribed in the upper half plane and the lower half plane, they are actually same. So that's why you are getting the net volume to be equals to 0, right? Just read this question first, that find the volume of the solid bounded by the elliptic paraboloid x square plus twice y square plus z equal to 60, planes x equal to 2 and y equal to 2, and the 3 coordinate planes. So see, you have I think read this question well, so I will just discuss it. So here your rectangular region is 0 to 2 to 0 to 2, the solid is above R, and this is elliptic paraboloid x square plus 2y square plus z equals to 16. So if you just integrate it in between 0 to 2 and 0 to 2, and your expression for z is 16 minus x square minus 2y square dx dy, you just integrate it, you will get it as 48. This is one more theorem, that let fxy be a continuous real valued function on a region R if R is given by a less than or equal to x less than or equal to b, and g1x is less than or equal to y less than or equal to g2x, where g1 g2 are continuous, then this R you can express it from integration from g1x to g2x. Similarly, if h1 similarly if the limit of x is also given in the in terms of y, then also you can write it as h1y to h2y. So find the volume of the prism whose base is the triangle in the xy plane bounded by the lines y equals to 0, x equals to 1 and y equals to x, and whose top lines in the plane z equal to 3 minus x minus y. So we are to find out the volume of the prism whose base is the triangle in the xy plane bounded by the lines x equals to 0, y equals to 0, x equal to this, and whose top lies in this. So our area of domain of integration is first x equals to 0 to 1, x equals to integration so if you just find the volume of this prism whose base is the triangle this is y equals to 0, x equals to 1 and y equals to x, and whose top lies in the plane z equal to 3 minus x minus y. So you have to just integrate from, see, the limit of x from will be 0 to 1 and the limit of y will be from 0 to x. So it is the functional expression for, and eventually you will get it is the functional expression for z, that z is 3 minus x minus y. So if you integrate, first you integrate with respect to dy. So if you integrate with respect to dy, you will get 3y minus xy minus y square by 2, right? Now you put the limit 0 to x, you will get 3x minus x square minus x square by 2. So minus x square by 2 will give you minus 3x square by 2, and 3x minus 3x square by 2, you take integration from 0 to 1, you will get it as 1. Similarly, it is just, you can also use the another form, that you are taking integration from the integration y you are taking from 0 to 1 and integration x you are taking to y to 1 to cover up the entire triangle. You will still it will still give you the values as equal to 1. These are some schematic expression, that how you are to determine this type of sectorial area and all. Okay, see, for evaluating a double integral as an iterated integral, choose some order first x and next y. If it does not work or if it is complicated, you may have to choose the reverse order. Okay, that what does it tell? First, for solving a iterated integral, try in the usual order. First integrate with respect to x, next integrate with respect to y. But if it does not work or it is too much complicated to handle, then you may choose the reverse order. So this is so see, xy, our limit of integration is y varies from 0 to 1, x varies from y to 1. So 0 to 1 and y to 1, sin x by x dx dy, no way to proceed further, we are stuck here. But if you just change the order of integration, that you take from x from 0 to 1 and y from 0 to x. See, so if you first integration with respect to dy, what you will get, y and x, it will eventually end up you getting sin x by x, and this is c, this is 0 to x dy, it is just dy means it is x, so you will get a sin x and you will get 1 minus cos 1, very easy. Similarly, just evaluate the iterated integral 0 to 1 x1 sin y square dy dx. See, evaluate the iterated integral this. So you are to try to determine the sin y square dy dx, and your triangular area is nothing but 0 less than or equal to x less than or equal to 1, x less than or equal to y less than or equal to 1. We plan to change the order of integration. How we will change the order of integration? How we will change the order of integration? See, that it is x to 1 sin y square. So see, this is how you are computing. You are computing like x varies from 0 to 1, it is covering this part, and then y varies from x to 1, so this is covering this part. Now similar approach you can take it like this, that this y varies from 0 to 1 and x varies from 0 to y. Now you just take integration, see how much easier it is, just half into 1 minus cos 1. So that is how order of integration works. Change the order of integration works. There is some like concepts here regarding that how to handle Riemann sum in polar coordinates. I will upload the note, no worry, I will upload the notes. You just go through it, that how you are constructing these things, that how you are constructing the mesh in the polar coordinate, and in the r theta plane how you are handling these things. So I will simply start solving some problems, that find the limits of integration for integrating f r theta over the region r that lies inside the cardioid this and outside the circle x square plus y square 1. Okay, so r equal to 1 plus cos theta, this is the cardioid, and this cardioid is, what is this cardioid? This cardioid is actually, this cardioid, see, this cardioid is actually a heart shaped curve. This is called cardioid. So this is a circle, and if you integrate this cardioid and circle, this sectorial area inscribed in between them, so first you put r equal to 1. So if you put r equal to 1, so cos theta equal to 0, so it is cos theta equal to 0. So cos theta equal to 0 means theta equal to minus pi by 2 and theta, other theta is pi by 2. So there are two roots. There are two roots. So if you just integrate it from minus pi by 2 to pi by 2, this 1 plus, and this is actually, this is c, here r equal to 1. So how this is varies? This is varies from r equal to 1 to 1 plus cosine theta. Now if you just integrate it from 1 to 1 plus cos theta and f r theta and the Jacobian matrix, the point to be noted that for when you are taking integration this in rectangular orbit, this dA is dx dy, but in polar coordinate, this dA is r dr d theta. This is r dr d theta. And caution is, do not forget the r on the right hand side. Similarly, integrate this. See, we can think of this root over 1 minus x square equal to y. So we can think this as the circle inscribed on the first coordinate, right? So if you think it as circle inscribed inside the first coordinate, you will get this is r varies from 0 to 1 and theta varies from 0 to pi by 2. That is how you can inscribe this sectorial area. So and your, if you just use polar coordinates, so this is x equal to r cos theta, y equal to r sin theta, and dy dx will be r dr d theta. So r varies from 0 to 1, theta varies from 0 to pi by 2, and r square into r will be r cube. So r cube dr d theta, this is pi by 8. So how you are determining this area to be pi by 8? So like this is the integration as pi by 8, pi by 8. This question is also very similar. I equal to minus 1 to 1, x equals to y equals to 0 to root over 1 minus x square. Just put that you are minus 1 to 1, so your theta varies from minus pi to pi, theta varies from 0 to pi, so that this is theta varies from 0 to pi, and r varies from 0 to 1. This is nothing but e to the power r square, r dr d theta, and this is the thing. Also, if you are to determine the inscribed area in between two circles, how to handle two circles? Here there is smaller circle is x square plus y square equal to 1. Here that is bigger circle x square plus y square equal to 4. So just your domain of integration is r equal to 1 to r equal to 2, and the theta varies from 0 to pi, so that you can cover the here to here. So this is 3r cos theta, x equal to r cos theta, plus y equal to r sin theta. It will be 4r square sin square theta, r dr d theta. So you first integrate with respect to r, and if you integrate with respect to r, you get 3r, and r it will be 3r square, so r cube cos theta plus 4r square into r means 4r cube, r to the power 4, 1 to 2. This is 7 cos theta plus 15 sin square theta, and if you now integrate with respect to d theta, you will get 15 pi by 2. Find the area enclosed by one of the 4 leaves of the curve r equal to cos theta. So this is actually a leaf type of pattern, and here your theta varies from minus pi by 4 to pi by 4. The region is from minus pi by 4 to pi by 4, and this is 0 to cos theta, and here you have to just determine the inscribed area. So you have to just integrate r dr d theta. So if you just integrate r dr d theta, you will eventually end up that this area of one leaf is pi by 8. So there are total 4 leaves. So how much area does they inscribe? They inscribe a total 4 into pi by 8, that means pi by 2 area. So find the volume of the solid that lies under the paraboloid z equal to x square plus y square above the xy plane, and inside the cylinder x square plus y square equal to 2x. So find the volume of the solid that lies under paraboloid this above xy plane, inside the cylinder this. So how you want to determine this? This is the case actually. See, this is a bit complicated problem. So the solid lies above the disk D, whose boundary has equation x square plus y square equal to 2x. In polar coordinates, r square equal to 2r cos theta, or r equal to 2 cos theta. So r lies between 0 to 2 cos theta, and theta lies between minus pi by 2 to pi by 2. uh, you just integrate it. It is z equal to r square. So r square into, so x square plus y square is you want to integrate. So this will give you r cube dr d theta. So that is all. That I will not start triple integral today, but I will not start triple integral today. I will stop here precisely. So till now the takeaway from today's class is we have learned how to solve multiple integrals using like iterated integral, the concept of iterated integrals, Fubini's theorem, like all. So this Fubini's theorem is very important for your perspective. This type of, first we have determined, let's be easy, first we have determined that how to determine this volume of revolution, this type of concepts. Now this is actually Fubini's theorem. This Fubini's theorem is very much important because it actually guides you, it actually gives you the relationship between multiple integral and iterated integral, and also when you are permissible to change the order of the integration, right? So Fubini's theorem is very important for our perspective, because it gives relationship between double integral and an iterated integral and also it gives us relations that when you can change this iterated integral, the order of the iterated integral, that the sufficient condition is that the function should be continuous. So whenever you get the function to be continuous, you just can use iterated integral, and that is how you can solve these things. Okay, so I will upload the notes. No worries, I will upload the notes. You try to determine these integrations taking suitable function fxy, expression for fxy. This picture is actually very useful for you. This picture tells you that how you can like interplay between the order of the integration and all. Also we have discussed some problems that when like iterated integral is useful, okay, when iterated integral is useful, that if you are determined to complicated integrals, then iterated integrals helps you. Okay, there are also some formulas that if fxy and gxy are continuous on a domain and c be a constant, then you can keep this c outside the integral sign. And also the integration case, like differentiation case, this like you can like the multiple integral of addition and sum is equal to the addition and subtraction of individual components. And also there is concept of additivity. That means if D interunion R, D and R are non-overlapping, that means they don't have any area in common, then you will get the additivity formula. Also domination is there, that if fxy is less than or equal to gxy in D, then this multiple integral will be less than or equal to D. And what is area? The concept of area is just you have to integrate 1 with respect to dA, and dA is dx dy, and in polar coordinate it will be r d theta dr, right? Then we have expressed concept of Riemann sum in polar coordinates, how to determine this type of sectorial area using polar coordinate concepts. The notions are very similar to what we have learned in see this type of complicated integrals. You can easily solve them using r theta coordinate plane. So r theta coordinate plane gives us flexibility. That r theta coordinate plane that gives us flexibility. You can if you have complicated function in x and y, if you use the polar coordinate, and polar coordinate will give you, will enable you, that polar coordinate will enable you to tackle the issues in a more, like in a more easier way. So that's the flexibility that polar description actually gives. So that's all for today's class. In the next class I will start discussing about triple integrals. There are many more things regarding triple integrals, and we will discuss them slightly. Then we will discuss some problems also. There are many problems. Okay, so that's all. Thank you all. Hope you all have a nice week ahead. That's all.